What if the universe held magnetic forces so intense they could twist space-time itself? These cosmic powerhouses exist, and they're not just science fiction. From the crushing grip of magnetars to the invisible web of magnetic fields stretching across galaxies, the universe is filled with extreme magnetic phenomena that defy imagination. In this video, we'll uncover 50 astonishing facts about these incredible forces that shape stars, power black holes, and even influence the birth of planets. Whether you're a space enthusiast or just curious about the mysteries beyond our world, you're about to embark on a journey that will leave you in awe of the universe's hidden wonders. So let's dive in and explore the universe's most extreme magnetic fields. You won't believe what's out there. Now turning to the first astonishing fact, let's explore magnetars, the cosmic titans of magnetic power. Imagine a magnetic field so intense it could erase your credit card from halfway across the galaxy. This is the reality of magnetars. These neutron stars are the remnants of massive stars that have collapsed under their own gravity, packing the mass of our sun into a sphere no larger than a city. What makes magnetars truly extraordinary is their magnetic fields, which are trillions of times stronger than Earth's. To put this into perspective, if a magnetar were located as close as the Moon, its magnetic field would strip the electrons from every atom in your body. But the story doesn't end there. Magnetars are born from the violent deaths of massive stars in supernova explosions, and their intense magnetic fields can wreak havoc across the cosmos. These fields are so powerful that they can disrupt electronics and satellites thousands of light years away, making them both fascinating and formidable. As we peel back the layers of these magnetic marvels, it becomes clear why they are considered some of the most extreme objects in the universe. Now shifting our focus to the next astonishing fact, let's uncover the dramatic connection between magnetars and gamma-ray bursts, some of the universe's most powerful explosions. Gamma-ray bursts are intense flashes of energy that can outshine entire galaxies for a few fleeting seconds, and magnetars play a pivotal role in these cosmic fireworks. The incredible magnetic fields of magnetars, trillions of times stronger than Earth's, can trigger these bursts in a process known as magnetic reconnection. This occurs when twisted magnetic field lines snap and realign, releasing an enormous amount of energy in the form of gamma rays. Unlike typical gamma-ray bursts, which are often caused by the collapse of massive stars or collisions between neutron stars, those linked to magnetars are fueled by the sheer power of their magnetic fields. These bursts can send shockwaves through the surrounding space, heating up interstellar gas and seeding the cosmos with heavy elements. The impact of these events is profound, as they can influence star formation and even shape the evolution of galaxies. Magnetars, with their magnetic might, continue to reveal the intricate ways in which the universe generates and disperses energy, making them a cornerstone of astrophysical research. Now turning to the fascinating mechanisms behind neutron stars, let's explore how these cosmic powerhouses generate their astonishing magnetic fields. Neutron stars, including magnetars, are born from the remnants of massive stars that have undergone supernova explosions. As these stars collapse, their cores compress into an incredibly dense material made primarily of neutrons. This process not only reduces the star's size to roughly the diameter of a city, but also amplifies its magnetic field to extreme levels. The rapid rotation of neutron stars plays a crucial role in this magnetic amplification. Imagine a figure skater pulling in their arms to spin faster. Similarly, as the star's core collapses, its rotation speeds up dramatically, which in turn intensifies its magnetic field. Additionally, the dense materials within neutron stars, composed of exotic particles like neutrons and protons in a superfluid state, contribute to this magnetic powerhouse. These particles generate electric currents that interact with the star's rotation, creating magnetic fields trillions of times stronger than Earth's. This combination of rapid spin and dense core materials makes neutron stars some of the most magnetically extreme objects in the universe. Understanding these processes not only sheds light on the nature of neutron stars, but also helps us unravel the broader mysteries of magnetic fields in the cosmos. As we delve deeper into the universe's magnetic marvels, it's clear that neutron stars are key players in shaping the cosmic landscape. Shifting our gaze closer to home, let's explore the magnetic field of our very own star, the Sun. While it may not rival the extreme strength of a magnetar, the Sun's magnetic field is no less dynamic or influential. Unlike the concentrated, ultra-strong fields of neutron stars, the Sun's magnetic field is generated by the churning motion of charged particles within its plasma-filled interior. This process, known as the solar dynamo, creates a complex web of magnetic loops and patterns that stretch across its surface and extend far into space. One of the most dramatic effects of the Sun's magnetic activity is the production of solar flares and coronal mass ejections. These are massive eruptions of energy and charged particles that occur when magnetic field lines become twisted and suddenly snap, releasing an immense burst of radiation and matter. These events can have significant impacts on Earth's magnetosphere, the protective magnetic bubble that surrounds our planet. When a coronal mass ejection reaches Earth, it compresses the magnetosphere and triggers geomagnetic storms, which can disrupt satellites, power grids, and even communication systems. On the brighter side, these interactions also produce stunning auroras, as charged particles collide with gases in the Earth's atmosphere. Understanding the Sun's magnetic field not only helps us predict and mitigate the effects of space weather, but also provides a window into the behavior of stars across the universe. As we continue to study these magnetic phenomena, we gain deeper insights into the forces that shape both our solar system and the cosmos beyond. Now venturing deeper into the cosmos, let's turn our attention to one of the most fascinating and mysterious phenomena in the universe, black holes. While they are often celebrated for their immense gravitational pull, black holes also possess magnetic fields that play a crucial role in shaping their behavior and their surroundings. These magnetic fields are generated by the swirling motion of charged particles within the accretion disks that orbit black holes. As matter spirals inward, it becomes highly energized, creating intense magnetic activity. One of the most striking effects of these magnetic fields is their ability to launch powerful jets of particles into space. These jets, which can stretch for thousands of light years, are thought to be formed when magnetic field lines twist and snap, channeling particles outward at nearly the speed of light. These jets are so energetic that they can influence entire galaxies, heating surrounding gas and even regulating star formation. Additionally, black hole magnetic fields play a key role in shaping their accretion disks. By influencing the flow of matter and energy, these fields help determine how quickly material is consumed by the black hole and how much is ejected into space. This delicate balance between gravity and magnetism reveals a dynamic interplay of forces that continues to challenge our understanding of the universe. As we study these magnetic fields, we uncover not only the secrets of black holes, but also the broader processes that drive cosmic evolution. Now shifting our gaze closer to home, let's explore the magnetic field of our very own Milky Way. Unlike the intense, localized fields around objects like black holes or magnetars, the Milky Way's magnetic field is vast and intricate, stretching across the entire galaxy. This field is generated by the movement of charged particles within the galaxy's disk, particularly in regions where stars are actively forming. Though it's relatively weak compared to the extreme fields we've discussed, measuring about 1 million times weaker than Earth's magnetic field, it plays a critical role in shaping the galaxy's structure and evolution. One of its key functions is guiding the movement of cosmic particles, such as high-energy protons and electrons. These particles spiral along the magnetic field lines, which acts as a cosmic highway, directing their paths across the galaxy. Additionally, the Milky Way's magnetic field influences the formation of stars. As clouds of gas and dust collapse to form new stars, the magnetic field helps regulate this process by opposing the force of gravity, slowing the collapse and ensuring a more controlled formation. Without these magnetic fields, star formation would be far more chaotic, and the galaxy as we know it might look drastically different. This delicate balance between magnetic forces and gravity not only shapes our galaxy, but also offers a glimpse into the interconnected nature of cosmic phenomena. Understanding the Milky Way's magnetic field helps us piece together the larger story of how galaxies evolve and thrive over billions of years. Now turning to the cosmic cradles where stars are born, let's explore how magnetic fields play a pivotal role in star formation. When vast clouds of gas and dust in space begin to collapse under their own gravity, magnetic fields step in to shape this process. These fields thread through the clouds, acting like invisible scaffolding that resists the gravitational pull, slowing down the collapse and ensuring that stars form in a more orderly fashion. Without this magnetic resistance, the collapse would be chaotic, leading to an uneven distribution of material and potentially disrupting the delicate balance needed for star birth. As these clouds continue to collapse, the magnetic fields also help channel the material into rotating disks around the forming stars. These protoplanetary disks are the birthplaces of planets, and the magnetic fields within them influence how matter clumps together, eventually forming planets and other celestial bodies. In some cases, these fields can even launch powerful jets of material from the young star, shooting out into space at incredible speeds. This interplay between gravity and magnetic forces isn't just about creating stars, it's about setting the stage for entire planetary systems to emerge. By regulating the flow of material and shaping the structure of these disks, magnetic fields ensure that the process of star formation is both controlled and efficient, giving rise to the diverse array of stars and planets we see throughout the universe. Understanding this intricate dance helps us appreciate how magnetic fields are not just passive observers but active participants in the grand story of cosmic creation. Now shifting our gaze closer to home, let's explore Earth's own magnetic field and its critical role in shielding our planet from the harsh realities of space weather. Earth's magnetic field acts like an invisible force field, extending far into space and providing a protective barrier against the constant stream of charged particles emitted by the Sun. Without this magnetic shield, our atmosphere would be stripped away over time, and life as we know it would struggle to survive. One of the most stunning effects of this magnetic interaction is the creation of auroras, those mesmerizing displays of light seen near the polar regions. When solar particles collide with Earth's magnetic field, they are funneled toward the poles where they interact with gases in the atmosphere, producing the vibrant colors of the northern and southern lights. However, our magnetic field isn't invincible. During periods of intense solar activity, such as solar storms or coronal mass ejections, the Sun can unleash massive bursts of energy that stretch and distort Earth's magnetic field. These events can disrupt satellites, interfere with communication systems, and even cause power outages on the ground. Understanding the dynamics of Earth's magnetic field helps us prepare for and mitigate the impacts of these cosmic disturbances, ensuring that we can continue to thrive in the face of space's unpredictable forces. This delicate balance between protection and vulnerability reminds us of just how connected we are to the vast and ever-changing cosmos. Now turning our attention beyond Earth, let's dive into the fascinating magnetic fields of other planets in our solar system. Jupiter, the largest planet, boasts an incredibly powerful magnetic field, about 20,000 times stronger than Earth's. This immense field is generated by the churning metallic hydrogen deep within Jupiter's core, creating a magnetosphere so vast it stretches millions of kilometers into space. This magnetic shield not only protects Jupiter but also influences its numerous moons, particularly Io, where the intense interaction drives volcanic activity unlike anything seen elsewhere in the solar system. Saturn, on the other hand, has a magnetic field that's slightly weaker than Jupiter's but still formidable. Its magnetosphere is unique because it aligns almost perfectly with the planet's rotation axis, a rare phenomenon among planets. Saturn's magnetic field plays a crucial role in shaping its iconic rings and affects its moons, especially Enceladus, where magnetic interactions hint at the presence of a subsurface ocean. These planetary magnetic fields aren't just impressive in their own right, they also shape the environments of their moons, offering clues about potential habitability and the dynamic processes at work in our cosmic neighborhood. Understanding these magnetic fields helps us appreciate the complexity and diversity of planetary systems, reminding us that each world is a unique laboratory of cosmic forces. Now shifting our gaze to the outer reaches of the solar system, we encounter Uranus, a planet with a magnetic field that defies expectations. Unlike most planets, where the magnetic field aligns closely with the rotational axis, Uranus' magnetic field is tilted at an extreme angle of nearly 60 degrees. This peculiar orientation means the planet's magnetic poles are located closer to its equator than its actual poles. Scientists believe this unusual configuration stems from Uranus' unique internal structure, where the magnetic field is generated not in the core but in a layer of electrically conductive fluid higher up in the planet's interior. Another fascinating aspect of Uranus' magnetic field is its interaction with the solar wind. As charged particles from the sun stream past the planet, they create a dynamic and asymmetric magnetosphere, one that shifts and wobbles with the planet's rotation. This chaotic interaction can lead to intense auroras and other magnetic phenomena, though they are not as easily observed as those on Earth. Uranus' magnetic field serves as a reminder of the incredible diversity of planetary systems and the mysteries that still await discovery in our cosmic backyard. Each world, with its unique magnetic signature, offers a glimpse into the complex processes shaping our universe. Now venturing deeper into the cosmos, let's explore the fascinating world of pulsars, a remarkable type of neutron star. Pulsars are born from the remnants of massive stars that have undergone supernova explosions, leaving behind incredibly dense cores. What makes pulsars truly extraordinary is their intense magnetic fields, which can be up to 1 trillion times stronger than Earth. These magnetic fields channel beams of radiation, often in the form of radio waves, X-rays, or gamma rays from the pulsar's magnetic poles. As the pulsar spins rapidly, sometimes hundreds of times per second, these beams sweep across space like the light from a cosmic lighthouse. This regular pulsing effect is how pulsars earned their name and allows astronomers to detect them even from vast distances. Pulsars are also incredibly precise in their timing, making them invaluable tools for studying the universe. For instance, they've been used to test theories of gravity and even to detect gravitational waves. Their role as cosmic lighthouses not only helps scientists map the galaxy, but also provides insights into the behavior of matter under extreme conditions. Each pulsar, with its unique rhythm and magnetic signature, adds another piece to the puzzle of the universe's most extreme magnetic phenomena. Now shifting our gaze to our neighboring planet, Venus presents a curious mystery when it comes to magnetic fields. Despite being nearly the same size as Earth, Venus lacks a robust global magnetic field like the one that protects our planet. The reason lies in its slow rotation. Venus takes about 243 Earth days to complete a single rotation, which is far slower than Earth's 24-hour spin. This sluggish rotation means Venus doesn't generate the same dynamo effect in its core, a process crucial for creating a strong magnetic field. Without this protective shield, Venus is left vulnerable to the relentless bombardment of solar wind, a stream of charged particles from the Sun. This has had profound effects on the planet's atmosphere and surface. The solar wind has stripped away lighter molecules over billions of years, leaving behind a thick, toxic atmosphere dominated by carbon dioxide. The lack of a magnetic field also means Venus experiences extreme surface temperatures, soaring to nearly 900 degrees Fahrenheit, hot enough to melt lead. These harsh conditions make Venus a vivid example of how magnetic fields play a critical role in shaping a planet's environment and habitability. As we continue to study Venus, its magnetic shortcomings offer valuable lessons about the delicate balance that allows a planet to thrive or wither in the vast expanse of space. As we broaden our perspective beyond individual planets and stars, let's delve into the vast magnetic fields that stretch across entire galaxies. These cosmic magnetic fields are far more than just a backdrop. They play a crucial role in shaping how galaxies evolve and function. Imagine a galaxy not just as a collection of stars, gas, and dust, but as a dynamic web of magnetic forces that influence everything from star formation to the movement of cosmic particles. These fields are not uniform. They twist and turn, creating intricate patterns that can stretch for thousands of light years. One of the most fascinating ways we detect these galactic magnetic fields is through synchrotron radiation, a type of electromagnetic emission produced when high-energy electrons spiral around magnetic field lines. This radiation allows astronomers to map out the invisible magnetic structures within galaxies, revealing how they interact with other elements of the cosmos. Magnetic fields also play a key role in regulating the flow of gas within galaxies, which in turn affects the birth of new stars. As gas clouds collapse under gravity, magnetic fields can either speed up or slow down this process, acting as a cosmic brake or accelerator. Additionally, these fields help shape the spectacular jets of particles that shoot out from the centers of some galaxies, powered by supermassive black holes. By studying galactic magnetic fields, we gain deeper insights into how galaxies grow, change, and interact with their surroundings. These fields are a subtle yet powerful force, weaving their influence through the fabric of the universe itself. Now shifting our focus to the smallest planet in our solar system, let's explore the intriguing magnetic field of Mercury. Despite being just a fraction of Earth's size, Mercury boasts a magnetic field that has puzzled scientists for decades. Compared to Earth's robust magnetic shield, Mercury's field is much weaker, about 1% as strong. This faint magnetic field is thought to be generated by a process similar to Earth's, involving the movement of molten iron in its outer core. However, Mercury's small size and slow rotation make this process far less efficient. What's truly fascinating is how Mercury's magnetic field interacts with the Sun's intense radiation. The planet orbits closer to the Sun than any other, enduring blistering solar winds and extreme heat. Despite its weak magnetic field, Mercury manages to deflect some of this solar radiation, creating a small magnetosphere that protects its surface, though not as effectively as Earth. Scientists believe Mercury's magnetic field is also influenced by the planet's unique geology and history. Unlike Earth's relatively stable field, Mercury's may have undergone significant changes over time, possibly even reversing its polarity. Studying Mercury's magnetic field not only helps us understand the planet itself, but also provides insights into how magnetic fields behave in extreme environments. As we continue to gather data from missions like NASA's MESSENGER, we uncover more clues about the complex interplay between Mercury's magnetic field and its harsh surroundings. This tiny planet's magnetic field may be weak, but its story is anything but small. Now stepping into the realm of cosmic exploration, let's uncover how magnetic fields shape the journey of cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, originating from sources like supernova and other violent cosmic events. But as these particles race across the universe, they don't travel unimpeded. magnetic fields act as invisible guides, bending and redirecting their paths in ways that can either protect or expose celestial bodies. For planets like Earth, our magnetic field serves as a shield, deflecting many of these particles away from the surface. Without this protective barrier, cosmic rays could bombard our atmosphere, potentially disrupting ecosystems and even posing risks to life. However, not all planets are so fortunate. Mars, for instance, lost its global magnetic field billions of years ago, leaving it exposed to the full force of cosmic radiation. This has significant implications for the planet's atmosphere and any potential for future human exploration. Beyond planetary protection, magnetic fields also play a crucial role in space travel. Astronauts venturing beyond Earth's magnetosphere face increased exposure to cosmic rays, which can pose health risks over long durations. Understanding how magnetic fields interact with these particles is vital for designing safer spacecraft and developing strategies to shield astronauts during deep space missions. Interestingly, cosmic rays themselves can even generate weak magnetic fields as they move through space, creating a complex web of interactions that scientists are still unraveling. By studying these phenomena, we not only learn how to protect ourselves but also gain insights into the broader workings of the universe. Magnetic fields, though invisible, are powerful forces that shape the paths of cosmic rays and, in doing so, influence the safety and exploration of space itself. Now shifting our focus to the red planet, let's delve into the intriguing story of Mars' magnetic field. Once upon a time, Mars had a global magnetic field similar to Earth's, generated by the movement of molten materials in its core. Evidence of this ancient magnetic field is preserved in the planet's crust, where magnetized rocks tell the tale of a once active magnetic dynamo. However, billions of years ago, something changed. Mars' core cooled and the dynamo shut down, causing the magnetic field to fade away. Without this protective shield, Mars became vulnerable to the solar wind, a stream of charged particles from the Sun. Over time, the solar wind stripped away much of Mars' atmosphere, transforming it from a potentially habitable world into the cold, barren planet we see today. This loss of atmosphere had a profound impact on Mars' climate, leading to the evaporation of liquid water and the freezing of its surface. The absence of a magnetic field also means that Mars is constantly bombarded by harmful cosmic radiation, which poses significant challenges for any potential life past or present. For future human exploration, this radiation exposure is a major concern, as it could endanger astronauts and complicate efforts to establish a sustainable presence on the planet. Scientists are now investigating whether remnants of Mars' ancient magnetic field could be reactivated, or if artificial magnetic shields could be developed to protect future missions. Understanding Mars' magnetic history not only sheds light on its past, but also informs our strategies for exploring and possibly colonizing this enigmatic world in the future. Now turning to the vast expanse of distant star systems, let's explore the fascinating realm of exoplanets and their magnetic fields. Exoplanets, which orbit stars outside our solar system, are not just intriguing for their potential to host life, but also for the magnetic fields that may surround them. While detecting these fields is incredibly challenging, astronomers have developed innovative methods to study them from Earth. One key technique involves observing how exoplanets interact with their host stars. When a planet's magnetic field deflects charged particles from its star, it creates a detectable signal in the form of radio emissions or changes in the star's light. These subtle clues help scientists infer the presence and strength of a magnetic field. Magnetic fields play a crucial role in a planet's ability to support life. Just as Earth's magnetic field shields us from harmful solar radiation, an exoplanet's magnetic field could protect its atmosphere from being stripped away by stellar winds. This protection is essential for maintaining stable conditions, such as liquid water and a hospitable climate, which are vital for life as we know it. One notable example is Proxima Centauri b, an exoplanet located in the habitable zone of its star. While its magnetic field hasn't been directly observed, scientists speculate that it could have one, making it a prime candidate for further study. The study of exoplanetary magnetic fields is still in its early stages, but advancements in technology, such as more powerful telescopes and sophisticated detection methods, are bringing us closer to unlocking these mysteries. By understanding how magnetic fields influence the habitability of exoplanets, we gain valuable insights into the conditions needed for life beyond Earth. As we continue to peer into the cosmos, each discovery brings us one step closer to answering the age-old question: are we alone in the universe? Shifting our gaze to one of Jupiter's most intriguing moons, Europa presents a cosmic mystery that continues to captivate scientists. This icy world, with its smooth surface crisscrossed by reddish cracks, hides a secret beneath its frozen exterior, a magnetic field that hints at something extraordinary. Through observations made by spacecraft like Galileo, researchers have detected fluctuations in Europa's magnetic field. These variations suggest the presence of a conductive material beneath the ice, most likely a vast subsurface ocean of salty water. This ocean, kept liquid by tidal forces generated by Jupiter's immense gravity, could potentially span the entire moon, holding more than twice the volume of Earth's oceans combined. The implications of this discovery are staggering. A subsurface ocean on Europa, shielded by a thick layer of ice, might offer one of the most promising environments for life beyond Earth. The magnetic field not only indicates the ocean's presence, but also plays a role in protecting it from intense radiation emitted by Jupiter. This protection creates a potential haven for microbial life or even more complex organisms, thriving in the dark depths where energy could be derived from hydrothermal vents or chemical reactions. The idea of life existing in such an alien environment challenges our understanding of habitability and fuels our curiosity about the possibilities hidden within our own solar system. Future missions such as NASA Europa Clipper aim to unlock these secrets by studying the Moon's magnetic field in greater detail and searching for signs of plumes erupting from beneath the ice. These plumes could carry samples of the ocean to the surface, offering a glimpse into what lies below without the need to drill through miles of ice. As we prepare to explore Europa further, the magnetic field serves as a guiding beacon, pointing us toward one of the most exciting frontiers in the search for extraterrestrial life. What we discover here could redefine our place in the universe and bring us closer to answering the profound question of whether we are truly alone. Now venturing into the explosive realm of supernova, we uncover the critical role magnetic fields play in these cosmic detonations. Supernova, the colossal explosions marking the death of massive stars, are not just random bursts of energy. Magnetic fields within these stars act as crucial drivers, shaping the intensity and direction of the explosion. As the star collapses under its own gravity, its magnetic field intensifies, channeling energy outward in powerful jets. These jets, guided by the magnetic fields, can propel the star's outer layers into space at incredible speeds, creating the spectacular displays we observe. But the influence of magnetic fields in supernova extends far beyond the explosion itself. They also play a pivotal role in the distribution of elements throughout the universe. During the explosion, heavy elements like iron, gold, and uranium are forged in the star's core and ejected into space. The magnetic fields help scatter these elements across vast distances, seeding galaxies with the building blocks of planets, moons, and even life. Without these magnetic forces, the distribution of elements might be far less uniform, potentially altering the chemical makeup of the cosmos. This process underscores the interconnectedness of magnetic fields and the evolution of the universe. By shaping supernova explosions and dispersing essential elements, magnetic fields contribute to the cosmic cycle of creation and destruction. As we continue to study these phenomena, we gain deeper insights into how the universe's most extreme magnetic fields influence not only individual stars but the grand tapestry of existence itself. Now shifting our gaze to the enigmatic moon of Saturn, Titan, we explore the fascinating interplay of magnetic fields in this distant world. Unlike most moons, Titan does not possess its own significant magnetic field. Instead, it interacts with the powerful magnetic field generated by Saturn itself, creating a unique dynamic that shapes its environment. As Titan orbits Saturn, it moves through the planet's magnetosphere, a vast region dominated by Saturn's magnetic influence. This interaction induces a weak magnetic field around Titan, which acts as a protective shield against the solar wind. However, this shield is not constant. It fluctuates as Titan's position changes, exposing the Moon to varying levels of charged particles from Saturn's magnetosphere. These magnetic interactions have a profound impact on Titan's atmosphere, one of the densest among moons in the solar system. The induced magnetic field helps to stabilize the atmosphere by deflecting harmful solar radiation and energetic particles. This protection plays a crucial role in maintaining the complex chemical processes occurring in Titan's nitrogen-rich atmosphere, including the formation of organic molecules, which are essential building blocks for life. Moreover, the magnetic interactions influence Titan's surface in subtle but significant ways. The influx of charged particles from Saturn's magnetosphere can trigger chemical reactions in Titan's icy crust, potentially altering its composition over time. These processes may contribute to the formation of Titan's vast lakes and rivers of liquid methane and ethane, creating a landscape that is both alien and eerily familiar. By studying the magnetic relationship between Titan and Saturn, scientists gain valuable insights into how magnetic fields shape the environments of celestial bodies. Titan serves as a natural laboratory, offering a glimpse into the complex interplay of forces that govern the atmospheres and surfaces of moons and planets beyond our own. As we continue to unravel these mysteries, we inch closer to understanding the broader role of magnetic fields in the cosmos. Now stepping into the realm of the unseen, we delve into the intriguing connection between magnetic fields and one of the universe's greatest mysteries, dark matter. While dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes, scientists believe that its presence might leave subtle imprints on the magnetic fields that permeate the cosmos. This theoretical link offers a potential pathway to uncovering the secrets of this elusive substance. Magnetic fields are thought to interact with dark matter in ways that could leave detectable signatures. For instance, if dark matter particles possess even a tiny electric charge, their motion through cosmic magnetic fields could generate faint signals that astronomers might observe. These interactions could provide clues about the distribution and behavior of dark matter, helping us map its presence across galaxies and galaxy clusters. Additionally, the evolution of magnetic fields in the early universe might have been influenced by dark matter. Some theories suggest that the gravitational pull of dark matter played a role in shaping the large-scale structure of the universe, including the formation of magnetic fields. By studying the patterns and strengths of these fields, researchers hope to trace back the influence of dark matter during the universe's formative stages. One of the most exciting possibilities is that magnetic fields could act as a cosmic magnifying glass, revealing the presence of dark matter in regions where it would otherwise remain hidden. For example, the bending of magnetic fields around massive objects such as galaxy clusters could indicate the gravitational effects of dark matter. This approach could complement other methods of dark matter detection, such as gravitational lensing, opening up new avenues for exploration. As we continue to probe the mysteries of dark matter, the interplay with magnetic fields offers a promising frontier. While much of this remains theoretical, Advancements in observational technology and computational models are bringing us closer to understanding how these two fundamental components of the universe might be connected. Each discovery brings us a step closer to unraveling one of the cosmos's most profound enigmas. Now shifting our gaze to the outer reaches of the solar system, let's explore the magnetic field of Neptune, a planet that shares some fascinating similarities and striking differences with its neighbor, Uranus. Like Uranus, Neptune's magnetic field is highly unusual, both in its orientation and its behavior. While most planets, including Earth, have magnetic fields roughly aligned with their rotational axes, Neptune's magnetic field is tilted at an angle of about 47 degrees, making it one of the most off-kilter in our solar system. This peculiar tilt creates a magnetosphere that is dynamic and ever-changing, as the planet's rotation constantly shifts the magnetic poles relative to the solar wind. What makes Neptune's magnetic field even more intriguing is its offset from the planet's center. Unlike Earth, where the magnetic field originates near the core, Neptune's magnetic field is generated much closer to the surface. Scientists believe this off-center dynamo is caused by the unique composition and movement of its icy interior, where electrically conductive fluids deep within the planet generate magnetic forces. This unusual setup results in a magnetosphere that behaves quite differently from those of other planets, with complex interactions between the magnetic field and the surrounding space environment. Neptune's magnetosphere is also shaped by its interactions with the solar wind, the stream of charged particles emitted by the Sun. Due to the planet's tilted and offset magnetic field, the magnetosphere is highly asymmetrical, with regions of intense activity where the solar wind compresses the magnetic field and other areas where it stretches out into a long tail. These interactions can lead to the creation of auroras similar to those on Earth, but with a unique structure influenced by Neptune's magnetic peculiarities. As we continue to study Neptune's magnetic field, it offers valuable insights into the diversity of planetary magnetism and the complex processes that shape the atmospheres and magnetospheres of icy giants. Comparing Neptune to Uranus helps us understand how similar planets can develop such distinct magnetic behaviors, shedding light on the intricate interplay between a planet's interior, its rotation, and its interactions with the Sun. This exploration of Neptune's magnetic field not only deepens our knowledge of the outer solar system, but also highlights the incredible variety of magnetic phenomena that exist across the cosmos. Now venturing into the vast expanses of star clusters, let's uncover how magnetic fields play a pivotal role in these dense gatherings of stars. Star clusters, whether they're open clusters with loosely bound stars or globular clusters packed tightly together, are not just random collections of stars. They are dynamic systems where magnetic fields exert a significant influence. These fields, though often weaker than those around individual stars like magnetars, still shape the behavior and evolution of the stars within the cluster. Magnetic fields in star clusters can affect the movement of gas and dust, the building blocks of new stars. As these materials swirl and condense, the magnetic fields can either slow down or channel their flow, influencing where and how new stars are born. This process is particularly fascinating in young star clusters, where intense magnetic activity can lead to the formation of multiple stars in close proximity, creating a bustling stellar nursery. Over time, these magnetic interactions can also determine how stars move within the cluster, shaping its overall structure. Another key role of magnetic fields in star clusters is their impact on the life cycle of stars. Within these clusters, stars are often born in turbulent environments where magnetic fields can accelerate or decelerate their evolution. For instance, magnetic forces can trigger the collapse of gas clouds, leading to the birth of massive stars that burn brightly but die young. They can also influence the way stars interact with each other, sometimes causing stars to merge or be ejected from the cluster entirely. These magnetic interactions contribute to the diversity of stars we observe in clusters, from tiny red dwarfs to massive blue giants. The study of magnetic fields in star clusters also reveals how these systems evolve over billions of years. As stars age and die, their magnetic fields can leave behind remnants like neutron stars or white dwarfs, which continue to interact with the cluster's magnetic environment. These remnants can create complex magnetic patterns, influencing the behavior of younger stars and even the next generation of star formation. This ongoing interplay between magnetic fields and stars ensures that star clusters remain dynamic and ever-changing cosmic laboratories. By exploring the role of magnetic fields in star clusters, we gain a deeper understanding of how these systems form, evolve, and contribute to the broader structure of our galaxy. It's a reminder that even in the densest regions of space, magnetic forces are at work, shaping the universe in ways that continue to astonish and inspire. Now turning to the distant reaches of our solar system, let's explore the surprising discovery of a magnetic field around Pluto. Once considered a quiet, icy world on the edge of our planetary neighborhood, Pluto has revealed itself to be far more dynamic than we ever imagined. Scientists were stunned to find evidence of a magnetic field surrounding this dwarf planet, a feature that challenges our understanding of small celestial bodies. This magnetic field, though weak compared to those of larger planets, suggests that Pluto might still harbor unexpected secrets beneath its frozen surface. The origin of Pluto's magnetic field is particularly intriguing. Unlike Earth, which generates its magnetic field through a molten iron core, Pluto's interior is thought to be a mix of rock and ice. Some scientists believe that a subsurface ocean, kept liquid by the heat from radioactive decay or tidal forces, might be the source of this magnetic activity. If this is true, it would mean that Pluto joins the ranks of icy moons like Europa and Enceladus as a potential candidate for harboring liquid water, and possibly even the conditions for life. The implications of Pluto's magnetic field extend beyond its interior. This field interacts with the solar wind, the stream of charged particles emanating from the Sun, creating a unique magnetospheric environment around the dwarf planet. These interactions can affect the movement of particles in Pluto's thin atmosphere, as well as its surface ice, potentially shaping its strange, heart-shaped features. Additionally, studying Pluto's magnetic field provides valuable insights into how small, icy bodies evolve in the outer solar system, shedding light on the processes that shape these distant worlds. The discovery of a magnetic field around Pluto is a reminder that even the smallest and most distant objects in our solar system can hold surprising complexity. It's a testament to the power of exploration and the endless mysteries waiting to be unraveled in the far reaches of space. As we continue to study Pluto and its magnetic field, we're not only learning more about this enigmatic dwarf planet, but also expanding our understanding of the diverse and dynamic nature of the universe. Now shifting our gaze beyond the boundaries of our solar system, let's dive into the vast expanse of the interstellar medium and the magnetic fields that weave through it. The space between stars is far from empty. It's a diffuse mix of gas, dust, and charged particles, all threaded by invisible magnetic forces. These magnetic fields may be weak compared to those of stars or planets, but they play a crucial role in shaping the cosmos on a grand scale. They act as cosmic sculptors, influencing the movement of gas and dust, guiding the formation of stars, and even shaping the birth of entire galaxies. Without these magnetic fields, the universe as we know it would look dramatically different. One of the most fascinating aspects of interstellar magnetic fields is how they're detected. Since these fields are invisible, scientists rely on the behavior of cosmic particles to map them. For instance, when charged particles move through these magnetic fields, they emit a type of radiation called synchrotron radiation. This light, often observed in radio waves, provides a cosmic fingerprint of the magnetic field's presence and strength. Another method involves studying the polarization of starlight, the way light waves align as they pass through magnetized regions of space. These techniques have revealed that magnetic fields are not only widespread, but also intricately connected to the structure of the interstellar medium. These magnetic fields also play a key role in the evolution of galaxies. They help regulate the flow of gas within galaxies, controlling how quickly stars form and how matter is distributed. In regions where gas clouds are collapsing to form new stars, magnetic fields can either slow down or accelerate the process, depending on their strength and orientation. They even influence the creation of cosmic filaments, the massive threads of gas and dust that form the universe's largest structures. By shaping these filaments, magnetic fields are fundamental to the cosmic web that connects galaxies across billions of light years. The study of interstellar magnetic fields is a reminder of how interconnected the universe truly is. From the tiniest charged particles to the largest cosmic structures, these invisible forces are at work, shaping the fabric of reality. As we continue to explore and map these fields, we're uncovering new insights into the processes that govern the birth and evolution of stars, galaxies, and the universe itself. Now turning our attention closer to home, let's explore the magnetic field of our nearest celestial neighbor, the Moon. Unlike Earth, which boasts a strong global magnetic field generated by its molten iron core, the Moon's magnetic field is much weaker and more localized. Scientists believe the Moon once had a stronger magnetic field billions of years ago, likely powered by a molten core that has since cooled. Today, remnants of this ancient field are preserved in certain regions of the lunar crust, creating pockets of magnetism that intrigue researchers. These localized magnetic fields are thought to have formed when the Moon's surface was bombarded by intense solar radiation and charged particles, magnetizing parts of the crust. Interestingly, these magnetic anomalies have been detected in areas known as lunar swirls, bright, swirling patterns on the Moon's surface. These swirls are not only visually striking, but also serve as a window into the Moon's magnetic past, offering clues about its geological and thermal history. The Moon's weak magnetic field has significant implications for lunar exploration. Without a strong global field, the Moon's surface is constantly bombarded by solar and cosmic radiation, posing challenges for astronauts and equipment. However, the localized magnetic regions could offer partial shielding in specific areas, potentially making them safer landing sites for future missions. Understanding the Moon's magnetic field is also crucial for unraveling its internal structure and evolution, helping scientists piece together how it formed and changed over time. As we continue to study the Moon's magnetic field, we're not only unlocking secrets about its past, but also preparing for humanity's return to its surface. These insights will shape how we explore and eventually inhabit our lunar neighbor. With the next phase of space exploration on the horizon, the Moon's magnetic mysteries remain a key piece of the cosmic puzzle. Now shifting our gaze to the far reaches of the cosmos, let's dive into the magnetic fields of quasars, some of the most luminous and energetic objects in the universe. Quasars are powered by supermassive black holes at the centers of galaxies, which devour surrounding matter and release immense amounts of energy. But what's often overlooked is the crucial role magnetic fields play in these cosmic powerhouses. The magnetic fields in quasars are incredibly strong, shaping the way matter falls into the black hole and influencing the formation of powerful jets. These jets, which shoot out from the black hole at nearly the speed of light, are fueled by the magnetic fields twisting and channeling charged particles into narrow beams. Without these magnetic fields, quasars wouldn't be able to produce such dramatic and far-reaching phenomena. What makes quasars even more fascinating is how their magnetic fields are detected. Scientists observe the polarized light emitted by these objects, which is a direct result of the magnetic field's influence. This polarized light provides valuable clues about the strength and structure of the magnetic fields, helping us understand how they contribute to the quasar's immense energy output. Interestingly, the magnetic fields in quasars aren't just confined to the immediate vicinity of the black hole. They extend far beyond, influencing the surrounding galaxy and even intergalactic space. This makes quasars not only brilliant beacons of light, but also key players in shaping the large-scale structure of the universe. By studying the magnetic fields in quasars, we're gaining insights into some of the most extreme environments in the cosmos. These magnetic fields not only power the dazzling light show of quasars, but also offer a window into the complex interactions between black holes, galaxies, and the universe itself. As we continue to explore these luminous giants, we're uncovering the magnetic forces that drive the most energetic phenomena in the cosmos. Now turning to the icy wanderers of our solar system, let's explore the magnetic fields of comets. As these frozen bodies journey closer to the Sun, they begin to heat up, releasing gas and dust that form their iconic tails. But what's less visible to the naked eye is the weak magnetic field generated during this process. As the comet's nucleus heats up, the released gas becomes ionized, creating charged particles that interact with the Sun's solar wind. This interaction induces a magnetic field around the comet, though it's much weaker compared to those of planets or stars. These magnetic fields play a fascinating role in shaping a comet's tail. While the dust tail is primarily influenced by the Sun's radiation, the ion tail, made up of charged particles, is directly shaped by the comet's magnetic field and the solar wind. This tail always points away from the Sun, no matter the comet's direction of travel, because the solar wind and magnetic forces push it outward. The interaction between the comet's magnetic field and the solar wind also produces stunning visual effects, such as the glowing plasma tail that can stretch for millions of kilometers. This tail is a direct result of the magnetic field channeling charged particles into streams that light up as they interact with the solar wind. Studying the magnetic fields of comets gives us valuable insights into the early solar system. Comets are considered remnants from the formation of our solar system, and their magnetic fields provide clues about the conditions and processes that were present billions of years ago. By analyzing these fields, scientists can better understand the composition and behavior of comets, as well as their interactions with the Sun's radiation and solar wind. As we continue to explore these icy travelers, we uncover not only the secrets of how comets generate their magnetic fields, but also how these fields shape the dynamic and beautiful phenomena we observe from Earth. As we shift our gaze to the grand tapestry of the universe, let's delve into the magnetic fields that thread through cosmic filaments. These immense structures, stretching billions of light years across, are the largest known formations in the cosmos, forming a vast network that connects galaxies like beads on a cosmic web. What's truly remarkable is that these filaments are not just empty space, they are permeated by magnetic fields, though incredibly weak compared to those found in stars or planets. These magnetic fields play a crucial role in shaping the evolution of galaxies. As matter flows along these filaments, drawn together by gravity, the magnetic fields influence how gas and dust accumulate, guiding the formation of stars and galaxies. Without these fields, the process of galaxy formation might look very different. Scientists believe that these magnetic forces help regulate the flow of cosmic material, preventing it from collapsing too quickly or dispersing entirely. But how do these magnetic fields form in the first place? One theory suggests that they were generated in the early universe, possibly during the Big Bang or through the turbulence of cosmic gas as structures began to form. Over billions of years, these fields were amplified and stretched as the filaments grew, becoming woven into the fabric of the universe itself. Studying these magnetic fields provides valuable insights into the large-scale structure of the cosmos. By observing how they interact with cosmic filaments, scientists can better understand the forces that shape the universe. This research also sheds light on the distribution of dark matter, which is thought to play a key role in anchoring these filaments. As we continue to explore the universe's largest structures, we uncover the subtle yet powerful influence of magnetic fields. From guiding the birth of galaxies to shaping the cosmic web itself, these fields remind us that even in the vastness of space, invisible forces are at work weaving the story of the universe. As we venture further into the wonders of our solar system, let's turn our attention to Io, one of Jupiter's most fascinating moons. Known for its extreme volcanic activity, Io is a world constantly reshaped by the immense forces at play. But what drives this relentless volcanic energy? The answer lies in its interaction with Jupiter's powerful magnetic field. Jupiter's magnetic field is the strongest of any planet in our solar system, and Io orbits right within its grasp. As Io moves through this magnetic field, it experiences what's known as electromagnetic induction. Essentially, the moon acts like a giant conductor, generating electric currents within its interior. These currents heat up Io's core, creating immense pressure that leads to widespread volcanic eruptions. The result is a moon that's covered in over 400 active volcanoes, making it the most geologically active body in the solar system. The constant eruptions spew lava and sulfurous gases into space, creating a thin atmosphere that's quickly stripped away by Jupiter's magnetic field. This process also contributes to the formation of a plasma torus, a ring of charged particles that encircles Jupiter along Io's orbit. The interaction between Io and Jupiter's magnetic field is a prime example of how magnetic forces can shape the physical characteristics of a celestial body. It's a dynamic relationship that not only fuels Io's volcanic activity, but also influences the broader environment around Jupiter. Studying Io provides valuable insights into the complex interplay between magnetic fields, planetary interiors, and surface features. As we continue to explore the magnetic mysteries of our solar system, Io stands as a testament to the incredible power of these invisible forces. Its fiery surface and tumultuous relationship with Jupiter remind us that even in the cold reaches of space, magnetic fields can ignite worlds. Now shifting our gaze to the remnants of once mighty stars, let's explore the magnetic mysteries of white dwarfs. These dense stellar cores, left behind after stars like our Sun exhaust their nuclear fuel, are not just inert relics of the cosmos. Surprisingly, many white dwarfs retain strong magnetic fields, a legacy from their earlier stages of life. When a star reaches the end of its life and sheds its outer layers, its core collapses into a white dwarf. During this process, the star's magnetic field can be preserved or even amplified. This happens because the magnetic flux, essentially the total magnetic energy, is concentrated as the star's core contracts. The result is a white dwarf with a magnetic field that can be thousands of times stronger than Earth's. These magnetic fields play a crucial role in shaping the evolution and behavior of white dwarfs. For instance, they can influence how the star cools over time, as magnetic fields can trap charged particles and slow down the loss of heat. This means that magnetic white dwarfs might cool at different rates compared to their non-magnetic counterparts, offering astronomers valuable clues about their internal structure and history. Moreover, the magnetic fields of white dwarfs can affect their surroundings. If a white dwarf is part of a binary system, its magnetic field can interact with its companion star, potentially altering the flow of material between them. In extreme cases, this interaction can lead to explosive events like nova, where the white dwarf's intense gravity pulls material from its companion, triggering a sudden burst of energy. Studying magnetic white dwarfs also helps scientists understand the broader life cycle of stars. By analyzing these objects, researchers can piece together how magnetic fields evolve from a star's birth to its final stages, providing insights into the magnetic processes that shape the universe. As we reflect on the enduring magnetic legacy of white dwarfs, it's clear that even in their quiet twilight years, these stellar remnants continue to influence the cosmos in profound ways. Their magnetic fields serve as a reminder that the universe's invisible forces are ever present, shaping the fate of stars and the galaxies they inhabit. Now turning our attention to the icy moons of Saturn, let's explore the fascinating magnetic interactions of Enceladus. This small, icy moon is a powerhouse of activity, with its famous plumes of water vapor and ice shooting into space from its south pole. These plumes are not just a spectacle, they reveal crucial insights into the moon's interior, particularly its subsurface ocean and its magnetic field. Enceladus's magnetic field is unique because it doesn't originate from the moon itself. Instead, it's generated through its interaction with Saturn's massive magnetic field. As Enceladus orbits Saturn, its icy surface and subsurface ocean conduct electricity, creating a weak but detectable magnetic response. This process, known as induction, allows scientists to indirectly study the moon's hidden ocean without ever landing on its surface. The plumes of Enceladus play a key role in this magnetic interaction. These geyser-like eruptions, driven by hydrothermal activity beneath the icy crust, send particles into space that become electrically charged when exposed to Saturn's magnetic field. This creates a dynamic magnetic environment around the moon, one that spacecraft like NASA's Cassini mission have been able to measure in detail. What makes this discovery so exciting is the potential for life. Enceladus's subsurface ocean, kept liquid by tidal heating from Saturn's gravity, contains the essential ingredients for life: water, energy, and organic molecules. The magnetic interactions not only confirm the ocean's existence, but also provide clues about its composition and potential habitability. By studying Enceladus's magnetic field and its plumes, scientists are piecing together the story of this icy moon's hidden ocean. It's a reminder that even in the outer reaches of our solar system, magnetic fields can reveal secrets about worlds that might harbor life. Shifting our gaze to the very beginnings of the cosmos, let's delve into the mysteries of how magnetic fields came to exist in the universe. The story of magnetic fields stretches back to the Big Bang, the explosive event that gave rise to everything we see today. While the Big Bang itself didn't produce magnetic fields, the conditions it created set the stage for their eventual emergence. In the early universe, as matter began to cool and form, tiny fluctuations in density and temperature created the perfect environment for magnetic fields to develop. These fields started on a minuscule scale, likely generated by the movement of charged particles in the hot, ionized plasma that filled the cosmos. Over time, as the universe expanded and structures like galaxies and stars began to form, these magnetic fields were amplified and shaped by the forces of gravity and motion. One fascinating theory suggests that magnetic fields were further strengthened by the turbulent processes occurring in the first galaxies. As gas and dust swirled and collapsed to form stars, the magnetic fields within these regions became more concentrated and organized. This galactic dynamo effect not only preserved these fields, but also helped spread them across vast regions of space. Today, magnetic fields permeate nearly every corner of the universe, from the smallest asteroids to the largest cosmic filaments. Their presence is a testament to the dynamic and evolving nature of the cosmos. By studying these fields, scientists are uncovering clues about the early universe and the processes that shaped it, offering us a window into the very fabric of reality. As we continue to explore the origins and evolution of magnetic fields, we're reminded of how deeply interconnected the universe is, with even the smallest forces playing a role in the grand cosmic story. Now, let's turn our attention to the future and the exciting advancements on the horizon for studying the universe's most extreme magnetic fields. Scientists and engineers are developing cutting-edge missions and technologies that promise to deepen our understanding of these fascinating cosmic phenomena. One of the most anticipated projects is the upcoming launch of advanced space telescopes equipped with highly sensitive magnetic field detectors. These instruments will allow us to map magnetic fields in regions of space that were previously inaccessible, such as the cores of distant galaxies and the edges of black holes. In addition to space telescopes, ground-based observatories are also undergoing significant upgrades. Facilities like the Square Kilometre Array, set to be the largest radio telescope in the world, will provide unprecedented detail about magnetic fields in star-forming regions and galactic structures. By combining data from these observatories with simulations run on next-generation supercomputers, researchers aim to uncover the intricate mechanisms that amplify and sustain magnetic fields across the cosmos. Another groundbreaking area of research involves the use of satellites designed to study the magnetic fields of planets and moons within our own solar system. Missions like the European Space Agency's Jupiter Icy Moons Explorer will explore the magnetic interactions between Jupiter and its moons, offering insights into the potential for life in subsurface oceans. Similarly, NASA future probes aim to investigate the magnetic environments of exoplanets, helping us understand how these fields might influence habitability beyond Earth. These advancements are not just about collecting data, they're about unlocking the secrets of the universe. By studying extreme magnetic fields, we're gaining a deeper understanding of cosmic processes, from the formation of stars and galaxies to the behavior of matter in the most extreme conditions. Each discovery brings us closer to answering fundamental questions about the nature of space, time, and the forces that shape our universe. The future of magnetic field research is bright, and with every mission, we're stepping into a new era of cosmic exploration. As we bring this cosmic journey to a close, let's take a moment to reflect on the incredible world of extreme magnetic fields in the universe. From the unimaginable power of magnetars to the subtle but vital magnetic fields of planets and moons, these forces shape the cosmos in ways we're only beginning to understand. They influence everything from the birth of stars to the behavior of black holes, and even the potential for life on distant worlds. Each of the 50 facts we've explored today reveals just how intricate and awe-inspiring these magnetic fields truly are, painting a picture of a universe filled with mystery and wonder. These discoveries remind us that the universe is far more dynamic and interconnected than we often realize. Magnetic fields are not just invisible lines of force, they are fundamental to the fabric of space and time, driving some of the most extreme and beautiful phenomena in existence. As we continue to develop new technologies and launch ambitious missions, our understanding of these fields will only deepen, opening doors to even more profound questions about the nature of reality itself. If you've enjoyed this journey through the universe's most extreme magnetic fields, don't forget to hit the like button and share this video with fellow space enthusiasts. Your support helps us create more content like this, unraveling the mysteries of the cosmos one fact at a time. And if you haven't already, subscribe to our channel and turn on notifications so you never miss out on the next cosmic adventure. The universe is vast and its secrets are waiting to be discovered. Let's explore them together. Thanks for watching, and until next time, keep looking.